各位喜欢科学的朋友们，大家上午好！欢迎大家今天上午来到中国科技馆，参加由中国数字科技馆和环球科学杂志社共同举办的科学连线活动。今天我们非常荣幸地请到了美国著名物理学家、麻省理工学院教授、2004年诺贝尔物理学奖得主弗兰克·维尔切克教授来到了活动的现场。他将为大家带来一场有关科学与艺术的精彩演讲。同时，我们今天还邀请到了北京大学量子材料中心的吴彪教授，美国匹兹堡大学与上海交通大学的刘文胜教授，中央电视台导演、主任编辑钟丽满老师，以及知名翻译家维尔切克教授新书《美丽之问》的译者蓝莓老师来到现场。他们会与维尔切克教授进行一个对谈，共同探讨科学与艺术的关系。今天来到活动现场的，还有中国科学技术馆的副馆长廖红女士。那么，在今天的活动开始之前，让我们有请廖红馆长为大家致辞。
大家上午好。今天呢，我们在中国科技馆的这个报告厅迎来了第2期科学连线的活动。首先，我代表中国科技馆真诚地欢迎维尔切克教授，欢迎吴彪教授、刘文胜教授、钟丽满导演以及蓝莓老师的到来，也欢迎各位嘉宾、各位朋友，让我们在一起共赴一场科学与艺术交流碰撞的科学盛宴。科学连线活动是由中国数字科技馆和环球科学杂志社联合举办，邀请世界知名科学家通过视频连线或者现场面对面的形式开展的一个讲座类型的活动。在这里，与国内的科学家和观众朋友们一起对话交流，帮助和带领大家更生动、更深入地了解前沿科学。我们非常高兴能够举办这样的活动。本期活动，我们荣幸地邀请到美国著名理论物理学家、2004年诺贝尔奖物理奖获得者弗兰克·维尔切克教授。他是量子色动力学的创立者之一，提出过轴子假说、时间晶体理论等，在现代物理学领域做出了重要的贡献。今天呢，他来到中国科技馆，做的是一场科普讲座。他不仅会和我们讲讲科学，还将从科学的视角带我们一起领略大自然的美，去发现世间万物的内在联系。同时，科学连线活动还会持续在中国数字科技馆的网站上与大家一起分享和回顾。中国数字馆是国家科技基础条件平台中一个科普平台，集成和整合了大量的优质科普资源。大家可以通过平台看到许多图文、音视频等科技知识以及科技热点，也可以通过在线游戏、移动 VR、实时互动展品参与体验科学。通过讲座、教育活动的发布、专题活动、直播等，融入中国科技馆丰富多彩的线上线下活动。也欢迎大家关注中国数字科技馆，参与到数字科技馆以及中国科技馆举办的各种活动当中。最后，预祝本次活动圆满成功，谢谢大家。
感谢廖馆长的精彩致辞。那么，现在今天的活动就正式开始了，让我们用热烈的掌声欢迎维尔切克教授上台。同时，我们也有请吴彪教授为我们同步做一些讲解。
大家早上好，我吴彪，来自北京大学。我在就是由于没有同声翻译，所以呢，我来担任那个维尔切克教授的翻译。
It's a pleasure to be here in this very beautiful museum and to see so many bright young faces and older thoughtful faces too.
就非常高兴来到这个那个漂亮的那个博物馆，见到这么多年轻的脸，也见到了很多那个久经岁月的那个。
So my subject today is very close to my heart. It's the meeting or the marriage of art and science.
今天我要讲的呢，是我一直非常关心的一个问题，就是科学和艺术的结合。
This is a vast subject. We could talk for many days about it, and have interesting things to say every moment.
这是一个非常广阔的那个话题，如果要谈的话，我可以谈好几天都不会停啊。
But I'm going to be very disciplined about this, and I've only chosen 3 subjects that I think I can present in a meaningful way in a relatively short amount of time.
由于时间的关系呢，所以我这里呢就只能那个克制下自己，只选择3个问题来讨论。
Then we will have an opportunity to have a panel discussion and questions from the audience that where we can explore things further and maybe in other directions.
我的报告以后呢，我们还会有那个 panel discussion 那个讨论，就那个，然后呢，我们可以那个来共同探讨一下这个艺术和科学。
So please be thinking actively and thinking about what you might like to explore further and ask us questions later on.
所以呢，请你在那个听报告的时候呢，就想一想你有什么问题要问，然后我们在报告结束以后可以来一起探讨。
In this lecture, I will discuss 3 things. I will discuss first why visualization is such an important tool in science.
在这个报告里面，我要讲3个问题。第一个呢，就是视觉化，为什么这个视觉化在科学里面是个非常重要的工具。
And then I will discuss the deepest themes that I think that emerge from our profound understanding of the physical world that we've achieved recently, and how they echo themes that have been very important to artists for centuries.
然后呢，我要讲一下我们物理界最近的一些发现。这些发现我会告诉你，就是说，其实和艺术也是非常有关联的。
And then finally, I will discuss the use of art in supplying metaphors for scientific concepts and connecting ideas that sometimes may seem very abstract and separated from daily life to our experience of daily life and all its significance.
就是我待会最后呢，我要讲一讲，就是在艺术里面，我们可以在艺术里面找到很多比喻、类比，来那个找到和科学呢进行类比的一些东西，用艺术呢来那个把我们科学上一些非常抽象的东西呢，和我们那个一些日常生活中联系起来。
So that the science comes alive and involves our whole being.
这样呢，我们科学就变得活灵活现，那个成为我们的一部分。
So let me begin the first part then, the discussion of visualization.
那我们开始第一部分。
Visualization is a way, I'll argue, of connecting our cognitive organs, the different parts of our mind.
就是视觉化，其实就是把我们的那个认知的这个感官给联系起来，各种各样不同的认知的感官联系起来。
A human brain, if you just look at it, looks like a big ball of jelly.
那个我们大脑看起来其实就像一个那个果冻一样。
But actually, scientists have learned that it contains many different parts that are like specialized organs.
但其实科学家发现，这个果冻其实可以分成很多部分，每一个部分呢都有不同的功能。
That each perform a separate function, similarly to the way your stomach and your liver perform different functions.
它每部分的功能呢，就像你人体的那个器官，比如说你的肝、你的那个肺，那个有不同的功能一样，那个大脑的不同部分呢也有不同的功能。
Very large parts of our brain are devoted to the processing of visual information.
我们大脑的非常大的一部分呢，是用来处理视觉信息的。
This is something that humans are amazingly good at, as people who've tried to design computer vision have discovered.
这是我们人类特别那个擅长的一个那个功能，就是视觉。人们曾经就说有那个就是人工智能曾经想模仿人的视觉，其实现在都那个不是特别成功。
So although computers have gotten better than humans at playing games like chess and Go, it's still the case that humans can see the world and get around in the world much better than any computer.
就说计算机已经可以在那个围棋那个国际象棋上打败人类，但是在视觉方面，那个计算机还比人差很远。
So we're very good at seeing patterns and organizing things that come in through our eyes.
就是我们非常擅长于那个认识各种各样的不同的那个形状，就是看见不同的就是我们的视觉是非常棒，能够看到各种各样的视觉，很容易辨别一些不同的东西。
On the other hand, in many applications of the mind to understanding the physical world, we have to deal with much more abstract quantities.
当我们那个要去描写那个现实世界的时候，我们有时候需要那个去处理非常抽象的东西。
Than we ordinarily encounter in our visual system.
他们经常呢就是那个不在我们的视觉那个范围之内，就是我们的视觉没法来认识它。
In dealing with those things, we have to use other parts of our brain that are good at logical processing and dealing with mathematical symbols and words.
这个时候呢，我们就需要用我们人那个大脑的另外一部分来处理这些抽象的那个思维，就是比如说这些数学符号。
And those parts of our brain speak a very different language ordinarily than the parts of our brain that deal with visual processing and treatment of visual information.
就是这部分大脑呢和我们那个处理视觉部分的大脑就非常不一样。
But both become much more powerful when they can work together.
但是这两部分如果结合起来呢，它们会就变得更加强大。
And that's why being able to visualize abstract concepts is such an important tool for discovery and creativity in science.
这也是为什么就是说把一些抽象的东西视觉化是科学里面一个非常重要的工具。
So here, for instance, is perhaps the most powerful kind of example of visualization of science. On the bottom, you see a rather abstract equation.
在这个那个屏幕的底下是一个非常抽象的数学公式。
And it's very logically precise. Our logical brain, that deals with symbols and language, can deal very easily with this.
就是人类处理那个抽象思维的部分呢，很容易就那个处理这下面就是说这个数学公式。
On the other hand, our visual processing centers that are so powerful can't do much with this.
但是我们的那个处理视觉的那部分大脑呢，却对它一点感觉都没有。
However, it's possible to translate the equation into a visual image.
但是呢，我们现在有办法把这个抽象的数学公式呢处理成一个图像。
As was discovered by the French philosopher mathematician René Descartes.
这是那个法国那个数学家笛卡尔发现的。
So just for a moment, let me explain what this is. We have an equation that involves two quantities A and B, we call parameters, and A and B have different values in the different squares. So this square is B equals minus 8, A equals minus 4, and so forth.
对，这是一个关于 x 和 y 的一个方程，在这个方程里面呢有两个参数 a 和 b， 所以呢你看不同的方块就是其实对应不同的参数 a 和 b。
So in each square we have a different equation because A and B are different.
所以呢，这个每一个方块其实就对应了一个不同的方程，这里面的 a 和 b， 因为它们的 a 和 b 不一样。
But then within each square we have x going along this way, measuring distances in this direction, and y measuring distances in this direction.
这个横轴呢是 x， 这个竖轴呢是 y。
And the points that satisfy the equation are the curve that you see in blue.
说满足这个方程的那个点呢，就是用这个蓝线描绘出来的。
Now, those details might seem a little overwhelming, but the big message is that instead of having an abstract series of symbols, now you have these curves which have a life of their own, which come to life because our visual system can make sense of these things and see patterns.
所以呢，这些抽象的公式通过这个坐标系呢，就变成了一个非常生动的图画。这样一来呢，我们的抽象思维和我们的视觉思维呢，就可以结合起来。
So now you can ask questions and see regularities and anomalies and strange behavior that you would have a very hard time seeing directly from the equation. Things like the curves falling into two pieces, or bending back and forth, or having a circle end a line, and so forth. All kinds of questions. Why do these things happen as you change A and B? Could you predict in advance how it might have happened? Open up once you allow yourself to visualize the abstract equations.
就是你看这个图上有很多非常那个奇怪的那个图形，比如说有些线，你看有一个圈，然后有一条线，然后分开的，有一个圈，然后有一条线就穿过去。这些东西你在看下面这个抽象的数学公式的时候，你是看不出来的。但是你通过把它画到一个坐标系里面，你就可以看得非常清楚，然后你可以去用你的脑子去想象它。
So this is the power of getting our brain, different parts of our brain, to speak a common language. That is the art and science of visualization.
所以呢，就是说让我们的大脑的不同部分结合起来，这就是把科学和艺术结合起来的这个视觉化的一个真髓所在。
And visualization is a powerful practical tool as well. When chemists study the structure of molecules and try to design molecules that are useful, that stick to each other and make useful reactions.
等化学家想设计一个分子的时候，这视觉化呢也会对他们有非常大的帮助，因为他们这样就可以直接就可以想象出来，我哪这个原子之间是怎么结合起来的，结合成一个化学键。
It's very important to know how the electrons are distributed, because the electrons are kind of the glue that holds different molecules together and are the sites of chemical reactions.
就是对于化学家来说，这个组成化学键的这些电子呢，到底是在哪个地方是非常重要的。这样的话，他就能够看到我到底哪里是有个很强的化学键，哪里是比较弱的。他就通过这个东西呢，我就可以把不同的原子组合起来，形成不同的分子。
And if the result of a calculation about where the electrons are likely to be is just printed out as columns of numbers, it's something that's very hard to work with.
就是说，其实科学家最早的时候在计算机上，如果是表达这个东西的话，其实无非就是一堆0和1而已。但是如果你把它画成这样一个画面以后呢，图像以后呢，你就这个分子呢就显得非常的生动了。
But if you put it into pictures like this, then you can visualize how you could get different molecules to stick together or cooperate to do useful things.
对，利用这种形象的图像呢，你就可以去想象我怎么把这些分子组合起来，组合成新的分子，有新的功能。
And you also see, as a bonus, that nature produces beautiful objects, as if nature is an artist.
而且从这里面也可以看出来这个是什么东西。你从这个图里面其实可以欣赏到，这个自然界其实是一个艺术家，因为它产生的这样的分子是如此的漂亮。
Of course, it takes a human to cooperate with nature to bring out the full beauty, to choose the right colors, to choose exactly the right shapes and sizes. But nature is an important collaborator in making these beautiful pictures.
当然，我们人类在画这些，在把这个自然视觉化的时候，我们也需要发挥一些我们自己的创造力，比如到底在什么地方用哪个颜色，哪个地方这个亮度怎么样，就是这是需要我们自己去发挥创造的。
At the frontiers of physics today, we learn a very remarkable thing that can be very difficult to visualize.
在现在物理学的前沿，我们发现了很多有意思的深刻的道理，很难去就是说去理解。
Which is that there's a lot of weather going on in space everywhere around us, all the time.
就像我们我们的空间到处都是各种各样的粒子。
This is called quantum fluctuations or spontaneous activity in empty space.
对，这是真空里的一个真空涨落。
If our eyes could resolve much faster times than they actually can, and much shorter distances than they actually can, we would see that everywhere in the whole universe, all the time, there's spontaneous activity. Energy concentrates and deconcentrates. There are fluctuations in the amount of electric charge, in color fields, and all the quantities of nature that are happening all the time in a kind of spontaneous activity.
就是如果我们的人眼看到非常小的距离，而且能分辨非常短的时间，那么我们其实在一个非常真空的一个非常空洞的空间里面，你能够看到很多自发的一些运动，能量聚集起来又扩散，就像这个图上画的这个样子。
So what we ordinarily see in everyday life as empty space is not really empty at all when you understand and visualize the equations that describe our deepest understanding of nature and our deepest understanding.
就说我们日常生活中看这个空的这个空间，其实有非常非常多的结构。就是我们物理学家是要用怎么我们是要用方程去描述它。但是如果你能够用像这张图画画出来的话，就能够展示这个空间里面这种掌握，这种自发的活动。
And importantly, this atmosphere that's all around us and these weather patterns very much affect the properties of the particles we do see.
对，就是我像这些真空的掌握，像有点像我们的气候一样，云的变化一样的，它其实会影响我们组成我们人大自然的各种基本粒子的活动性质。
So these pictures of different weather patterns give you some impression of how energy fluctuates in space.
这个其实向你展示的就是这个能量在这个真空里面是如何聚集和变异。
And here's a movie that makes the whole thing dynamic, where you can see where the colors are the brightest, that's where the energy is the biggest. And these kinds of calculations are not just to make pretty pictures, but to reveal the properties of matter.
这里给你展示的其实就是这样一个随着时间变化，这个真空里面的这些掌握是如何随时间变化的。他们这里这个科学家做的这个计算，不只是为了给你一个非常漂亮的图像，而且也是他们想去通过这个图像呢，去发现这个宇宙最深层的秘密。
So this picture is showing us what's happening inside a computer as it's modeling space to calculate the mass of protons and neutrons, and ultimately to understand our own mass.
这个计算呢，其实是科学家想在计算机里面模拟质子和中子的行为，然后去想通过这个计算机呢，去预言质子和中子的质量。
And because we get the right answer, we can be pretty sure that this is an accurate picture of what's going on in empty space, even if you don't see it.
就他们通过这些计算呢，就能够准确的预言质子和中子的质量，然后通过这个呢，也就可以验证，就是说我们描述这个世界的这个方程呢是正确的。
That is, we don't see it with our eyes, but with our minds and the help of artists and computers, we can bring out this inner beauty of nature.
就是我们看这个飞翔图像，其实你可以想象，其实是用我们的思维看到的。
So that's what I wanted to say about visualization. Now we'll turn to the deep themes that emerge from our most profound understanding of nature, symmetry and exuberance.
现在我们开始第二个话题，这是我们我们自然界一个非常深刻的一个道理，就是说对称。
That are also themes that humans and artists have embraced for many, many centuries before we knew that nature loved them also.
我们人类都非常喜欢对称，自然也很喜欢对称。
So, when we talk about symmetry in ordinary language, in everyday life, it has many different kinds of meanings. It means balance, it means harmony, it means generally good things, but to use it in science, we need a more precise concept.
在我们的日常生活中，对称可以是平衡，可以是和谐，各种各样的有意义。但在我们在科学上用这个对称这个词的时候呢，我们就必须给它一个比较严格的定义。
The concept that we found that captures sort of the essence of symmetry that's flexible and useful in science is what I've written here. Symmetry is change without change.
在科学里面，对称呢其实就是不变质变，就是说你改变一个东西，但其实它又没有改变。
That may seem very peculiar and almost mystical. Let me explain exactly what it means.
这个听起来好像很玄乎，但其实我马上给你解释的，其实非常容易理解的。
So think about a circle.
想象一个圆。
A circle is sort of the most symmetric object that you can have in two dimensions.
这个一个圆呢是在你的二维空间里面能够看到的最对称的物体了。
And what makes it symmetric is that you can rotate it around its center by any amount. And if you do that, every point on the circle usually moves, but the circle as a whole does not change.
这个圆之所以对称的原因，是因为你可以绕着它的那个圆心转，对吧？当你在转的时候呢，这个圆它的每一个点都在动，所以都在变，但这个圆其实没有变，这就是不变质变。
So there's a transformation that might have changed the figure, might have changed the shape, but in fact doesn't.
所以呢，就是说，你在转动这个圆的时候，你好像会改变它，其实又没有改变它。它的这个上面的每一个点的动，但它这个圆其实并没有改变。
And that's what makes it symmetric, the fact that allows you to change it without changing it.
所以对称就是这样，不变质变。你在好像你在改变它，但其实你在整体上并没有改变。
So a square, for instance, has some symmetry because you can't rotate it by just a little and get back to the same shape. But if you rotate by enough, if you rotate by 90 degrees, it comes back to the same shape. So a square has some symmetry, but less than a circle.
比如比如说还可以举一个例子，就是说正方形。正方形呢，它就没有圆这么对称，因为呢，正方形你不能转任何一个角的时候呢，它还是会发生一点改变的。你只有转90度，它就是你改变它的时候呢，最后它又回到以前，整体上又回到以前的形状。因为它都没有圆那么对称。
Humans have found symmetry extremely attractive across many, many cultures and across all of history and even before written history began.
人类发现这个对称是非常吸引人的，非常迷人的。
So if you look at catalogs of decorative design that are survey many cultures over time, you will find that going from Polynesian Indians to ancient China to the most sophisticated modern Art Deco, that symmetry in patterns is something that humans love to surround themselves with.
就是如果你去看看整个人类历史，去看看各个建筑物的内部的装饰，无论是哪个文化，你都会看到很多对称的图案。
And to play with. So, for instance, in this design, the change without change you can make is moving things up or down, and then the whole design goes over into itself.
比如说刚刚这个图形，你往上移动一定的距离以后，这个图形其实不会发生改变。
But in this one, the artist has played with it a little. If you move it over by 1, the shapes match, but the colors don't match. You have to move it over by 2 for the colors and shapes to match.
对这个图案来说的话，如果你只移动一格，这个由于这个颜色变了，所以它会改变。但是你如果移动2格，这个图案又没有发生改变。
And mathematicians and artists can have and collaborated and played with all kinds of patterns that are symmetric and can add both comprehensibility and interest by having variation.
就是艺术家和数学家都非常喜欢那个对称，他们设计了各种各样的这种对称图案。
So symmetry to have comprehensibility and variation to have interest.
就是他们这个图案呢，就是你看，虽然这个各个都是对称的，但是每个图案都有变化，这样让人觉得非常的更吸引人。
Symmetry, that concept of symmetry, I've shown you applies to shapes.
我刚刚跟你说的对称呢，是关于那个形状的。
But we can apply it much more generally to physical laws or to equations.
但这个概念呢，其实也可以推广到那个物理世界里面去描述方程，抽象的方程。
So, for instance, think about the idea that the laws of physics are the same everywhere through the whole universe.
就想一下吧，我们这个物理的那个就规律，在宇宙的各个地方都是一样的。
This is really a statement of symmetry, and that's the way we understand it in physics today. That's the most fruitful way of thinking about it.
这个其实就是一种对称，就是你物理规律在宇宙的任何一个角落都是一样的。
We call it translation symmetry, and it's the idea that if I move myself, make a change, the laws of physics don't change. I find the same laws of physics here that I found over there, and you'll have the same laws of physics wherever you are that apply to me, whether I'm here or there.
这种对称性叫那个平移对称性，就是你无论你走到宇宙的哪个地方，这个世界上这个宇宙的这个物理规律都是一样的。
Or the idea that the laws of physics are eternal and don't change with time is another symmetry. It means that if you imagine changing your position in time, you'll discover the same laws later that you observe today.
就是说那个时间上也是一样的，我们的物理规律不会随着时间而改变。现在成立的物理规律，明天也会成立。
And it was a great discovery that the same laws seem to apply everywhere and always. And now we understand that that has to do with their symmetry.
这个就是说，这是一个非常的一个重要的一个发现，就是我们发现我们那个知道的物理规律呢，是不随着空间和时间的改变的。
A more hidden use of symmetry is in the theory of relativity.
一个在那个狭义相对论里面呢，也有这种对称性。
Where the change you imagine is moving along at a constant velocity.
当你那个用一个就说一个元素运动的时候，当你元素运动的时候
And the statement of the theory of relativity is that the laws look the same. You have the same physical laws if you move along at a constant velocity as you would have if you were not moving.
就是说，那个狭义相对论其实就是说我一个物理规律不会随着你的运动的速度而改变。如果你的运动的速度是一个匀速的，那你在任何一个参照系里面，它都是一样的。
And that's a good thing because we know the Earth is rotating very fast around its axis, thousands of miles per hour, and the Earth is moving around the Sun also at a very rapid speed. If the laws of physics depended on the velocity, we would be noticing those motions, and who knows what would happen? Things would fly around in unpredictable ways.
这是一件好事情，为什么？你看，我们的地球自己在转，然后还在绕着太阳转，太阳本身也在那个运动， 所以呢，如果这个运动规律会随着你的速度而改变的话，那就会出大麻烦，就是你会发现这个地球上这个规律在不停的变化。
The full power of symmetry in guessing laws was discovered in the course of the 20th century when we discovered that the laws, when we had to guess laws for the new forces, the strong and weak force that were discovered inside atoms.
这些就是这个对称性在物理上的那个应用呢，是在20世纪的时候那个变得越来越明显。
And what physicists did was to guess, to propose that that the laws would have enormous amounts of symmetry, would allow many transformations that don't change their content.
就是物理学家现在经常会在做的一件事情呢，就是想象有更高的一个对称性，然后呢，然后在这个基础上呢，去那个推测有新的物理规律。
I won't explain those transformations in detail. They have to do with things like color charge and weak colors that would take a while to explain. But the unifying powerful principle is something called local symmetry.
就是我不会由于这个是涉及太多的数学，我不会来仔细讲。就是现在物理学家讲的这些对称性呢，其实一个更高的对称性，它会涉及到就是色核，还有洛色核这些非常抽象的一些概念。
Which is the idea that you allow yourself to make different transformations at different places in space and time, and the phenomena and the equations still have to look the same after you've made those transformations.
而且这个在物理学界呢，现在其实这个对称性不只是一个整体的对称性，还有那种所谓的局域的对称性，就是你在每个局部做一些对称变换，这个物理规律也不发生改变。
So not only can you move to a different place, or imagine moving yourself to a different time, or move at a velocity, you can make much more intricate changes in your picture of the world without changing how it works.
就是由于这个原因呢，所以你有更就说更多的选择，可以做更多的变化。然后呢，你这个物理规律还不会改变，因为你在每个局域都可以做不同的变化。
This is quite a wonderful idea.
这是一个非常奇妙的想法。
But it's also an idea that artists have used in the past when they've tried to express their notion of the divine and bring themselves into spiritual states.
这个想法呢，其实不只是科学家仅有的想法，这个艺术家其实以前也用过这种局域的对称性来就是表达自己对上帝、对各种神的敬仰。
Somehow to put themselves in harmony with reality.
通过这个呢，他们就可以和现实就说和谐相处。
So here, for instance, you see in this decoration of a mosque that many different symmetrical elements are used, different squares and pentagons and octagons, different regular shapes, circles of course.
这是一个清真寺内部的一个装饰，你可以看到它每个局域的对称性都不一样，对吧？它这不是整体有对称性，是每个局域有对称性。
But the symmetries of these objects are different. The circle here, you need to rotate around its center. The circle here, you need to rotate around its center. The square over here, you need to rotate around its center, and so forth. So the different symmetries are what we call local symmetries. You can apply them differently in different places in space.
你可以看到这个地方有不同的地方有不同的圆，所以你旋转的时候，你这里的圆只能绕自己的圆形转，另外的圆你绕到它自己的圆形转才会保持不变。然后有的地方呢是四方形，所以呢你只能转90度才会保持不变。
And the artist's intuition that somehow this is the way the world looks at its deepest level, or this is the way it's constructed, is actually correct.
所以呢，这个艺术家从这个意义上呢，他也发现了这个自然界的规律，就是说，他会发现，你看这样去构造这个教堂的话，清真寺的话就显得更美丽。
With a kind of precision, but also kind of expansion of meaning that the artist could only dimly anticipate.
当然，我们物理学家讲的这个对称性是艺术学家没有想过的。
Besides symmetry, I would say, as sort of complement or partner to symmetry, the other great theme that's emerged as our deepest understanding in 20th century science is a principle of exuberance. That is that putting, or sometimes called emergence, the idea that putting a lot of simple things together can give you something that has its own new properties and is beautifully intricate.
就是我现在要讲的一个，就是叫多姿多彩，就是说你把一些简单的东西放在一起，你会得到一些非常复杂的漂亮的东西。
So simple structures, simple ideas put together can give you wonderful emergent structure and control. Even though the beginning points are very simple, if you put enough of them together in creative ways, you can get something that's intricate and powerful.
尽管你的每一个那个构建都可能很简单，但是如果你想一种办法把它们放在一起，组合起来的话，它会变得非常非常的漂亮。
Now it's very interesting that this symmetry not only is consistent with exuberance and emergence, but actually powers it. Let me show you.
就这个对称性和这个多彩多姿其实那个相辅相成的，这是一个例子。
This is a fractal.
这是一个分形。
A picture made from a computer program.
这是一个计算机程序那个造出来的一个图像。
And I think you'll agree that it's very intricate and very beautiful.
我想你肯定那个同意，这是一个非常漂亮又非常复杂的一个图案。
And any artist that had invented this and would have been very proud, and rightly so, and very popular.
对，如果哪个艺术家发明了这样一个图像，他一定会变得非常有名的。
But the way it's actually made is starting from a simple picture with a range of colors. So actually made, I think in this case, from a bunch of rings or concentric circles.
但它其实这个图是怎么造出来的？就是在计算机上编了一个程序，然后从一个一个圆慢慢叠加，那个按照一定的规律叠加出来的。
And then performing a simple mathematical operation that moves the points.
然后呢，用一些数学的办法呢，把那个圆上的一些点移动。
Over and over again.
不停的重复。
Many, many times.
重复很多很多次。
So the computer program is very simple. You can write it in a few lines.
这个计算机的程序呢，其实只有几条，非常短。
But when you let the computer be the artist and just repeat this simple operation many, many times, it produces from simple ideas very rich content.
但是你让这个计算机按照这个程序进行简单的重复，它就能产生这样一个美丽的图画。
Of course, the human helps by picking the right colors and by judging when to stop. But this human mathematics, computer collaboration has produced a beautiful object.
当然，人类也做了贡献，就是人类选择了这里到底哪个地方用红色，哪个地方用蓝色。
That conveys a deep meaning that symmetry powers exuberance.
所以这种人、机器和数学的这种结合，就产生了这样一个美丽的图画。
Here's another fractal.
这是另外一个分形。
That was not made by a computer.
这不是计算机造出来的。
Or by anyone doing very elaborate calculations.
也不是哪个做数学的人做出来的。
Or image processing.
或者哪个图像处理师处理出来的。
This is just a rather stupid, mindless vegetable growing.
这只是一个蔬菜而已。
But the fact that it grows according to simple symmetrical rules, it only does the same thing over and over again.
但它你看它生长的那个明显是和计算机那是一样的，它就是同样一个东西不停的重复。
Allows it to blossom and make a very intricate, attractive pattern.
最后呢，就形成了这样一个非常漂亮的图画。
But if you examine this and think about it, you realize that what's been happening is these buds have been produced, and they grow, and new ones come up and push the old ones away. And according to these very regular laws and simple rules, following out their logic, you produce this extraordinary pattern that, again, I think any artist would have been proud to invent.
所以你看这边也是，你看每一个包都是一样的，然后呢，只不过是说我长出了新的，就是把其他的给放到旁边去，然后而且他们排列呢稍微是有些按照某种规律排出来以后，你看就变得这样非常的漂亮。
And the same idea happens for trees with a little more variation. You have growth and branching and growth and branching. And from small trees, the bigger tree looks like the small tree expanded. It's another kind of fractal.
这个树枝也是这样一个规律，就是它不停的分开，它这个也是在不停的重复，然后随之形成一个分形的图案。
And again, it's because the tree is not very smart and doesn't know how to do very many things that it produces these very symmetric yet beautiful and varied patterns.
所以呢，这个树呢，就说通过这种重复呢，也产生了这样一个非常漂亮的图像。
When humans want to make complicated objects that do useful things,
当人类要做一个非常复杂的事情，做一个非常有用的事情的时候
such as process information in powerful ways,
比如我们像那个非常强大的处理数据的能力。
as in this Intel chip, which is the core of many computers and processors.
这是一个Intel 的那个计算机芯片。
What they do is use simple physical units, transistors.
这里面它就是用一个非常简单的一个物理上非常简单的一个器件，叫那个晶体管。
In combinations, many of them, many identical combinations, cleverly wired up so that they can cooperate with each other.
所以这个芯片上无非就是有一堆非常完全一模一样的这个晶体管，连在一起。
And the efficient way to do that, again, is by making the patterns very, very symmetric. And you see these engineers who designed the computer chip were not thinking about making an artistic object.
你看从这个也可以看出来，就是说他们在连这些晶体管的时候，也是利用了对称性。他们在这个工程师在设计这个芯片的时候呢，他们没有想到要把它做成一个艺术品。
But the logic of making something that was comprehensible and orderly, and yet powerful because it contained many, many units, independent units, leads them to symmetry and leads them to very attractive artistic objects.
但是呢，他们为了让这个处理信息的能力更强大、更有效率，他们自然而然就想到了要用到对称性，就产生了这样一个那个芯片，看起来像一个艺术品一样。
So to me, this is even more beautiful than a Campbell's soup can.
这个比我那个 Campbell soup， 这个那个美国有一个食物叫 Campbell soup， 那个罐头，这个比那个要漂亮多了。
Now, finally, the third part of my talk, I'd like to discuss this idea that art provides metaphors that help us bring abstract scientific concepts that are given to us by nature into contact with everyday life.
就是艺术呢，还能给我们一个办法，就是这个 metaphor， 就是说比喻、类比的意思，就是能够把我们科学家发现一些抽象的东西呢，那个形象化，然后呢和我们这个现实生活联系在一起。
And this is very important for locating science within culture in general, and for enriching our lives through incorporation of scientific concepts.
这个呢是对于我们把科学和这个那个日常生活联系起来是非常重要的。
And it's also just fun to make these connections.
而且呢，就是你注意到这些艺术和科学的那些联系呢，其实往往是一个非常有意思的事情。
Bridges from deep reality to everyday experience.
这就是把那个我们物理学家发现的一些非常深刻的一些物理道理和现实联系起来。
So it's no coincidence, I think, that many scientists also have significant interest in drawing and art.
所以呢，这也不是一个奇怪的事情，就是说有很多科学家非常喜欢艺术。
So this is not an extract from the notebooks of Leonardo da Vinci. I have extracts from the notebooks of Leonardo da Vinci here on my tie. But this is extracts from notebooks of a modern great theoretical physicist, Richard Feynman.
这个图呢，不是那个达芬奇画，这是一个现代的物理学家范曼画。达芬奇画是在我的那个领带上。
So Feynman is perhaps not as great an artist as Da Vinci.
范曼呢，当然没有那个他的艺术能力没有达芬奇强。
But he was trying.
但他也那个试着尝试。
And got inspiration and pleasure from playing with human figures at the same time as he was playing with equations.
你看他在这里呢，他画的时候呢，下面还有很多那个抽象的一些数学公式，他其实在想把这两个。
And here you see, as you would find in pages of any scientist's notebooks, use of that tool of René Descartes that I told you about before for visualizing equations.
这里面你也看到了那个笛卡尔发明的一个坐标系，他用这个坐标系来把那个公式变得形象化。
Feynman himself introduced a new way of visualizing fundamental processes. I think his artistic inclinations came out in this form of creativity. He introduced a concept called a Feynman diagram.
范曼呢，他确实是在这个把科学变成视觉化的方面呢做出很大的贡献。这就是我们在那个粒子物里面有很多非常那个抽象的一些，比如粒子之间的一些反应。然后呢，范曼呢就发明了这个范曼图来表达这些粒子之间的反应到底是如何进行的。
So Feynman diagrams are sort of cartoons that break down elementary processes that occur in our fundamental theories of nature into a series of steps that can be visualized and put together. They tell a story. This is what's happening as time goes up here when reactions are happening in space.
那个范曼图其实就是将我们那个基本粒子之间的相互作用的形象化了。这个图呢，从下往上是这个时间的箭头，就是相当于这里有两个质子在碰撞，然后最后中间发生了一些物理过程，然后最后又产生两个质子。
This particular Feynman diagram is of some historical interest because it was key in discovering the Higgs particle, which was kind of a missing ingredient in our fundamental understanding of nature. And this discovery occurred only in 2012, after many years of searching.
这个非常特别的那个范曼图呢，有个意义在什么呢？就是说，物理学家就是利用这个范曼图表达这个物理过程，发现了 Higgs 粒子，在2012年。
And the process that was used is very complicated and would have been very difficult to think about if not for the tool of Feynman diagrams, which allows you to tell these stories. You see two protons come together, they interact by emitting gluons, which become quantum fluctuations of top quarks, which can communicate with the Higgs particle, which then very rapidly decays through other fluctuations, whether in vacuum, into photons, which is what you finally observe.
就这个过程其实非常非常复杂的，如果没有费曼图的话，你很难想象就说你在那个头脑里面把它想象成一个图像。但是有了费曼图以后呢，我们就可以来想象这样一个，把这个非常复杂的物理过程想象得非常清楚。两个质子是碰撞以后怎么变成胶质，整个出来那个真空涨落，然后在真空涨落里面出来Higgs particle，然后最后那个又形成两个那个质子出去。
Without these pictures, without these diagrams to hang it all together, it would have been very difficult to conceive of this.
我们如果没有费曼图的话，是很难想象这样一个过程。
But by keeping the pictures in mind, I was able to visualize and capture this on a walk one night at Formula.
但是有了这样一个形象图以后，我就会想，我就在有一天，我就在在费里那个晚上散步的时候呢，我就想到了这样一个过程，发现了这样一个过程，然后可以用来探测希克斯粒子。
Which helped lead to the discovery almost 40 years later.
就这个过程呢，就是我在那个时候呢，这其实是我40年以前做的，然后在40年以后，2012年他们就利用这个过程发现了这个希克斯粒子。
I love this metaphor. This is a painting by the British artist Turner.
这是英国画家 Turner 的一个画。
And it conveys, I think, the idea that light is a substance.
这里传递的一个意义呢，就是说光是一种物质。
In ancient times, and in fact, most people even today thought of light as quite distinct from matter, as something very different.
就是从在古代的时候呢，大家其实现在还有人认为呢，光和物质是不一样的。
But in modern physics, we have a unified understanding which treats light and matter in all its forms very much on the same footing, with the same kind of equations and the same kind of concepts.
但是现在的物理学家认为，光和物质是没有任何区别的，我们可以用统一的方式来描述它们。
So, for instance, we can think of light as made of particles named photons.
比如我们现在认为光其实是由光子构成的。
Still, to have the idea clearly in mind that light is a substance takes artistic imagination.
这个其实就是光是一个物质的一个艺术的表达。
The general theory of relativity, Einstein's understanding of gravity, is based on the idea that space itself can bend.
爱因斯坦的广义相对论的中心思想就是说，我们的时空其实是可以弯曲的。
Again, something that may be very difficult to visualize because we don't encounter it in everyday experience, and yet it's a deep aspect of reality that we'd like to bring to life.
这个当然我们在日常生活中从来我们也不会碰到时空弯曲，对吧？但是这幅画就告诉我们这个时空弯曲。
And artists in a technique called anamorphic art have enriched our experience of warping of space.
对，这种艺术呢，叫那种变形艺术，就是它把一个形状变了以后，这可以帮助我们来体会时空弯曲。
As I showed you before, our modern understanding of empty space, what looks like empty space, is that it's actually full of spontaneous activity.
就是我刚刚已经说了，我们的真空其实不空，我们的真空里面有很多自发的一种能量的聚集和消散。
So I love the idea that nature is constantly improvising and creating new patterns just for the fun of it.
所以呢，我非常高兴的，这个自然界每时每刻都在这种自发的产生各种各样神奇的现象。
As is captured in this artistic image.
然后这幅画呢，其实就是抓住了这种真空这种掌握的一种。
Which also brings in music.
这里也有音乐的里面。
So you can sort of hear it as well as see it.
对，所以你不但能看一看，你还能听到。
One of the most subtle and yet important concepts in modern physics and especially in engineering is the concept of superconductivity.
在我们物理学里面有一个非常神奇的现象，就是超导。
Ordinarily, when electrons move in metals, when they conduct electric currents, they encounter all kinds of obstacles and resistance.
一般情况下，当电子在一个金属里流动的时候，它会碰到各种各样的阻碍，所以呢，它会感受到电阻。
So their flow generates heat.
所以它们的流动呢就会产生热。
And is not very efficient.
所以呢，这样就会浪费很多能量。
And this causes many of our limitations on computing and power generation and so forth.
这也让我们呢在就说发电的时候呢，在我们设计电脑的时候遇到了很多困难。
But many materials when you cool them down enough to very low temperatures, enter a state called superconductivity.
但是呢，有很多材料，如果你把它放在一个很低温的情况下，它们就会超导。
Where the electrons all cooperate and move together and make a flow that pulls all of them together in the same direction.
在超导这个里面呢，这个电子就会互相协作，然后一起往前移动。
The equations are quite advanced and difficult to understand, but if you just think of yourself as a fish moving along with the flow of other fish, you capture the idea that because they're all doing the same thing and filling up space and cooperating, they all have to move together. And if there's any obstacle, they just flow nicely around it.
这个描述超导的这个方程呢是非常复杂的，但是呢，我们如果你要去理解一下超导的话，我可以把我自己想象成一条鱼，这个鱼呢，大家都在朝着一个方向运动。
So I like to sometimes think of myself as an electron when I'm thinking about how electrons will behave.
当我想描述那个电子的时候呢，我经常会把我自己就想象成一个电子。
But here I find not only if I want to think of myself as an electron, I also have to think of myself as a fish.
在这里当我把我自己想象成电子的时候，我经常把自己想象成一条鱼。
And this picture is very inspiring.
这个图像就是给了我很多启示。
Here from the notebooks of Leonardo da Vinci is a beautiful illustration of the idea that to understand things, we really have to look into their deep interior.
这是达芬奇的一幅画，这幅画就显示了，就是说，我们如果要理解一些那个物体的话，我必须找到它一些深刻的、隐含的一些结构。
That the secrets to the inner nature of matter are often hidden.
就是我们自然界里面的一些规律，经常是隐藏的。
But that if we want to do justice to what we do see, we should start by understanding things deeply in the interior.
对，所以呢，我们如果要理解这个自然界的话，我们必须就看更深刻一些。
So Da Vinci was very interested in portraying the human body accurately.
达芬奇呢非常想把人体呢画得非常准确。
In different circumstances.
在各种各样的不同的情况下把人。
And to do that, he thought it was very important to study corpses and dissect them and get accurate scientific knowledge of what's inside.
是他为了把人体非常的准确，所以他呢就去解剖各种各样的人体。
Okay, here's a beautiful object of meditation, again made from simple elements, repeated.
这是一个用来就是冥思的一个坐垫。
So this is inspiring when you're trying to think of creations, putting together the simple laws to do beautiful things.
这里就展示了你用简单的东西可以制造出一个非常复杂的图像。
This one is very close to my heart. What I got the Nobel Prize for is something called asymptotic freedom. Quarks and gluons, the basic ingredients of protons and neutrons and atomic nuclei, ordinarily can't exist as free particles.
这是我最喜欢的一幅画，因为这个和我得诺贝尔奖的那个发现关于夸克的渐进自由是非常相关的。
They don't exist in isolation. They are what we call confined.
这些夸克呢，它不能单独存在，它们是被禁闭在核里面。
So some people thought they couldn't exist. They didn't exist at all because you couldn't see them as elementary particles.
所以呢，很多人觉得这个夸克是不存在的，因为它没法自由的自己单独的。
However, if you put enough energy into matter and see how it interacts at high energy, you find that quarks and gluons get liberated, and although they don't exist as individual particles, they sort of set off explosions and fireworks that you can detect, and that's how their existence was proved, and now they're a very useful way of understanding the structure of matter.
就是虽然夸克不能单独存在，但是如果你用足够多的能量让那些粒子碰撞，它们就会把它就会造成了各种各样的它们就会飞出来，然后会造成各种的现象。通过它的这些现象呢，你就能够感受到这个夸克和胶水的存在。
So I discussed before the idea that empty space is actually a kind of atmosphere, and I love the idea that that atmosphere, which holds our protons and neutrons together, but also conditions the reality in which we live, is actually our friend and nourishes us.
如果一开始已经说了，我们的真空其实不空，这里面其实有点非常像一个大气一样，里面有各种各样的云在那个运动，就是这些就是自发的这些活动。然后这些活动呢，其实能够把我们这个质子啊、中子啊这些东西结合在一起。
So here somehow is Mother Nature being our friend and giving us nurturing.
刚刚那幅画就是这样一个，就是说那个自然这个母亲给了我们这些孩子，就是像那些例子一样。
So finally, I'd like to close with an image drawn by another great scientist. This is by Li Zhongguo.
这幅画呢是李政道先生画的。
Who was and is very fond of making artistic drawings.
李政道先生呢其实非常喜欢艺术。
That are very playful and elegant.
这幅画呢就写得非常的就是充满了童趣，然后也非常的优雅。
So here he's asking which came first, the chicken or the egg.
在这里面，他在询问到底是鸡和蛋，到底是哪个先出？
And if I understand the spirit of this, it's just to say, who knows, but we can have fun thinking about it.
没有人知道鸡和蛋是什么，但我们那个思考这个问题，给我们带来很多乐趣。
And so somehow this playful attitude that at the same time is serious and trying to do justice to nature's beauty is something that I very much admire, and I hope I've conveyed some of it to you today. Thank you.
这幅画展示的童趣和他同时又非常想深刻的理解这个自然的这个精神，这就是我今天要做报告的那个思想。
非常感谢维尔切克教授的精彩演讲，也非常感谢吴彪教授为我们做的这个讲解和翻译，让我们对宇宙和艺术的关系产生了全新的理解，对科学与艺术的关系产生了全新的理解，对宇宙万物也产生了全新的认知。那么下面呢，我们就进入今天的对谈环节。对谈将由知名翻译家，也是维尔切克教授新书《美丽之问》的翻译译者蓝莓老师来主持。然后接下来这个对谈环节的参与者还有美国匹兹堡大学教授、上海交通大学教授刘文胜，以及中央电视台的导演周黎满老师。现在我们请各位嘉宾再来到台上，我们把时间交给蓝莓老师。
听得见吗？
都没打开。
听得见吗？好。大家好，我是蓝莓，我有幸是维尔切克教授这本书《美丽之问》中文版的译者，我在这个翻译的过程中呢， 也学到了很多的知识。由于我不是物理专业的，不是学物理的，所以我请了北京大学的吴彪教授，为这本书做校正。吴教授呢是研究量子材料、凝聚态方面的，我们国家顶尖级的专家。吴教授的这个他的这个物理方面的学养，为这个我的这个译著增色不少，所以我非常的谢谢吴老师。我想呢，在这儿呢，接着刚才那个维尔切克教授的讲话，吴老师的翻译呢，为他补充一个方面吧，是刚才的那个 Campbell Soup Cans。Campbell Soup Cans 是美国波普艺术的一个代表作，它的作者可能大家的，我要说出名字来，大家都比较熟悉，叫安迪沃霍，翻译成中文应该是安迪霍霍尔。
对不起，所以我刚刚翻错了，因为我完全不了解的意思。
对，没关系，那个翻得非常的精彩，我们对这个，包括我自己在内，都对这个内容有了更进一步的理解。非常谢谢你。我想说的是，就是那个大家就这个作品，肯定应该大家在网上都能找到，就是50个那个罐头盒子，它画在了一幅画里面，是动物的盒子。那么拿这个和刚才的那个芯片做比较，可能我们就会觉得这个人类做出来的艺术和大自然的艺术比起来，可能稍稍的就弱了那么一点。所以我说这个科学是最伟大的艺术，因为是想这个在那个粒子加速器里用那个高能对粒子进行加速。我记得是在维尔切克教授那个书里面有，他是在地下27公里的那个轨道里面进行对撞。试想一下，哪一个人类的艺术家能做出这么伟大的装置艺术、观念艺术？所以我并不是说我们人类就不做艺术了，我们人类的艺术不行，而是说我们面对着大自然，面对着宇宙，要有这个感怀之心。好，我现在就说的这个。那么现在呢，我就这个几位这个嘉宾，他们各自的研究领域或者各自对宇宙和艺术的感受，我进行提问。Frank,
Yes.
I will ask you. You are the first to answer my question. I remember Paul Dirac used to say that mathematics is not the invention of human being. I can't remember the exact words, but he said something like that, similar. And when I did the translation of your book, I noticed that when you refer to a new theory or new equation, you usually like to use discover rather than create. So I want to know whether it is a humble way or there is some implication underlying the word. 我的第一个问题呢是想问维尔切克教授，是因为我在翻译他的这本著作的时候呢，发现了他有一个习惯，就是他每当说到谁或者他自己发现了一个做出了一个新的理论或者做了一个新的 方程，他不会用创造啊、发明啊，他只是说发现。所以我想问他的是，他总用发现，而不是用其他的，是一种谦辞呢，是一种谦卑的说法呢，还是说这个字、这个动词的里面有其他的含义？
Yes, so this question of whether equations or concepts are invented or discovered has many facets, and it's interesting. So it's sort of a problem of assigning credit when something beautiful emerges between nature and the human who elucidates nature. Do you want to translate that?
这是一个非常有趣的问题，就是关于是到底我们是发现了一个定理，还是创造了一个定理？这个问题呢有很多方面，这个方面就涉及到的一个事情呢，就是说我们当人类在和自然就是交流的时候，我们应该来如何描述这个？
And in my opinion, we should be generous and assign credit to both.
我认为呢，我们应该就是说，整个这个过程呢，我们应该既感谢就是说自然，也要感谢就是科学家。
So just as in photography, we recognize the creativity of the photographer, even though in some sense all they're doing is capturing nature rather than creating it.
对，比如即使是照相，对吧？就是说，虽然他只是用了一个相机把那个现实给照下来，但是那个摄影师本身他也是还有一些创造功能。
Nevertheless, insight in choosing what to make a picture of and how to present it adds to the discovery.
对，所以就说，你在照相的时候，其实你是在发现一个东西，但是你用哪个角度，你选哪一个那个图像的哪一个部分，这其实是你的创造。你这些创造呢，给这些图像呢增加了很多含义。
So, although I think the basic structure of our understanding of nature would have been the same, however, whatever the historical process that led to it.
所以呢，就是我们是一样的，就是说，那个自然界有很多一些基本的运动规律，但是这个历史上我们怎么去发现它的时候呢，其实是有很多不同的这个方面。
So in that sense, we're discovering things rather than inventing them.
所以从这种角度上来说呢，我们确实是在发现这些自然的规律。
Nevertheless, the actual works can be significant works of literature where the discoveries are announced, or if they're in pictures, they can be beautiful pictures.
但是你在你在做的这些发现的时候，你其实里面还是有很多图像可以，有很多故事，也有你在告诉别人你的这些发现的时候，你还可以用图像。
And the biographies of the discoverers can be inspiring and instructive.
就是这个每一个发现的过程，这个本身也是会非常的就是说具有教义，也会让你深受教育。
And so, just as a photograph conveys something of the personality of the photographer, so does the nature of the scientific discovery convey something of the personality of the discoverer.
就像你一个照相的一个摄影作品一样，摄影作品虽然是描述的是一个真实的世界，但是其实也反映了摄影师本人的一些创造和故事。然后我们对于这个自然界的这个发现整个过程呢也是一样的，就是说这个自然就是在那里，但是我们科学家在发现的这个过程中，也有他自己的创造性，也有他自己说生动的故事。
Thank you, friend. 所以就是说，一件东西是在那里，但是谁把它怎么解读，那要看那个解读的人，是这样的理解。
是的，我知道 ，this is my understanding. I think this is Frank's understanding.
那么我想问一下吴教授，您是这个维尔切克教授的学生，那么肯定跟他一起工作、一起学习，很近距离的接触，也很了解这个领域的发展。那么您认为从爱因斯坦到维尔切克，维尔切克对爱因斯坦有什么样的发展？
Translate. Yeah, go ahead.
Basically, he's asking Benjamin is your student, so he's asking about the experience working.
Yeah, she's asking a very broad question from Einstein to you, how the physics evolves, and she wants to see how I see from a person working under your supervision and guidance over the years. 我先给大家介绍一下我自己啊，因为我是在我跟吴边老师是在 Texas 的同学，后来我在 MIT 的时候是跟 Frank Wilczek 教授做博士后嘛。我的另外一个老师上也是吴边老师，在 Texas 那个 Steven Weinberg 嘛，都是些大的科学家。
就是李文跟伯格。
就是我刚才南美老师说的这个很重要，就是从 Frank, can you still understand what you're talking about?
No, it's all right. Go ahead.
I don't need to hear this.
就是说他这个问题非常重要，因为你会想啊，举个例子，我们现在像吴边教授的那个是量子产业中心，在北大开创这一个在国内一个非常创新的一个平台，聚焦在这一个题目上面。那你就从爱因斯坦当年，比如说100年前多一点点吧，1905年左右，比如说今天 Frank 提到了这个狭义相对论，对吧？然后也涉及到还有那个广义相对论了，包括前几年还有那个引力的探测，引力波的探测，对吧？你就会想，从过去那一代，比如说爱因斯坦到波尔爱因斯坦那个时代啊，海森伯格啊，这1920几年的时代，你就想到现在为止，物理学到底在做什么演变，对吧？那么 Frank 他们这个里面有一个什么样的贡献？我是这么看到啊。你看，在1905年的时候呢，到1920年代有2个很重要的发现，一个是比如说狭义相对论啊，还有这个量子力学，在1920年的时候，那么这个量子力学的发展呢，就导致了原子物理，对吧？所以今天 Frank 教授提到了那个原子的这个，比如说分子的结构、晶体，对吧？没有原子物理，就说没有量子力学，没有原子物理的身体理解，我们就不可能知道这个晶体结构啊，什么化学键。大家这些东西都不知道。那从把量子力学和狭义相对论结合呢，就导致了这个叫量子场论。最早是那个费曼还有一些别的老师，在叫量子电动力学，等于把这个狭义相对论和量子力学结合一起，就是量子电动力学。那么量子电动力学之后呢，就是对粒子物理更一步他们对人类自然的理解，也是对对称性更多的统一理论，就变成了量子弱电理论，就包括像斯蒂文·王伯格很多一些教授。那么 Frank Wilczek 他们教授就开始进来了，在1970年代就继续深入到核夸克这个层次，更深次。你看原子还是在10的负10次方这个量级，就是说0.1个纳米尺寸吧，对吧？那个尺寸。那么到了核呢，就是更小了。所以到了70年代就变成了量子，叫什么量子 QCD， 就什么量子射动力学。那么在 QCD 的这个情况，就是他们获诺奖的一个很重要的工作。所以你就发现，从一个宏观的，那以前是经典的物理，对吧？天体物理啊，那是在牛顿的时代。那么在1900几年，从爱因斯坦开始说起的话，就是把狭义相对论和这个量子力学的结合，就导致量子场论，导致了量子电动力学、量子弱电理论，到量子射动力学，那就涉及到原子，到了夸克的理论。所以人类对这个所有的理论了解很深，他们就是从爱因斯坦到 Frank Wilczek 这样一个很大的这个推进，就人类的认识从原子物理一直到夸克。那么他们一个重要的贡献就是夸克。那么现在你就想， Frank Wilshire 他们做什么，就是现在是讨论这个量子的前沿，就是说这种。
那么我还想问您一个问题，就是作为晚辈，以及您的晚辈，您对未来、对自己、对学生给予了什么样的目标和希望？就是在维尔切克的基础上，再有什么样的发展
？So she's asking an even broader question. So starting from the tower, my mentors built up your generation. What our generation, like Biao and myself, should do, and how we expect our next generation should do, like your academic grandson. What we should do. So she's asking me how to. You want to ask? Frank, you want to say something?
You want me?
Yeah, you go ahead. Yeah.
Well, I think there's more and better to do in physics now that we understand matter very well. We can turn to very ambitious questions. There are still questions about cosmology, how the universe began. The astronomers have discovered some very surprising things, so-called dark matter. So there are things in fundamental physics to be understood. But another thriving area is the application of the expanded view of the world that's emerged in recent years. The quantum world. We're now living through the second quantum revolution, which will enable new kinds of computers, new kinds of sensors, new kinds of clocks, new kinds of many things, where we have the knowledge to be very creative in fundamental new kinds of engineering, also that make contact with biological ideas. And so the future is extraordinarily open and for creativity in physics.
对，就说刚刚的问题就是说，我们年轻的物理学家还有什么事情可以做呢？那么是这个Frank Wilshire就是说，这有两个方面，比如说一个呢是基础的，比如说在宇宙，还有很多在宇宙的演化上，我们还有很多基本的问题没有理解，比如说暗物质，我们天文学家发现有这个暗物质，但我们还不知道这个暗物质到底是什么东西，所以这些很基本的问题我们还没有回答。另外呢，就跟我们日常生活有关的一点就是说，我们现在正在经历第二次量子革命，就是说我们现在已经对这个世界的这个物质有很好的理解，通过量子力学。但是我们这个量子力学还可以用来做很多新的就是应用，比如说新的计算机、新的感受器，甚至就是器，各种各样的一些用量子的新的技术，在这个方面呢。你说你是不用愁你的聪明才智没有发挥的地方。
对，我补充一下，刚才这个题目非常的好，因为年轻人好像学生特别多，对吧？包括像吴彪老师的学生都在清华做教授了，然后我的一个学生在复旦，那就相当于 Frank 的这个上一辈的这个下一代的弟子，对吧？就是我想你们也在问。大家还能做什么？我举一个例子吧，因为也是跟 Frank Wilshire 教授有关。他们 talk about the crystal。你知道他今天讲这个对称性，对称性的今天你看到是在空间的一种对称性。举个例子，你看啊，你的这个晶体实际上什么晶体是？比如说你的大家喜欢这个钻石就是你的碳原子在周期性的反应链。那么你做周期性平移的时候，他今天讲到了这个平移对称性，对吧？那么你就会发现它有一种很美的对称性。那现在最近他提出了一个很大的概念，就是这个叫 time crystal。那么你就想这个周期对称性，现在量子里面的时间对称性，时间的周期对称性是什么？你就想想这个答案嘛，就金刚石，对吧？钻石。那这么好的东西，如果是在时间里面的一个周期的，那是表示什么东西？因为还是遇到一个时间繁衍啊，东西，就是这些东西是没有认识的。就是换句话说是，可能 open 的问题、开放的问题比我们解决的还要更多了，对吧？也就是大家能够提出来的问题更多了，因为你知道的东西越来越多，提的问题可能问的越来越多。就是好像现在给我感觉量子力学不是已经结束了，就是刚才 Frank 和吴彪教授提到这个，就是说是面临着新的量子革命，
基本的框架是结束了。 但是它还有非常大的应用前景，它可能会带来更多新的技术和应用。
谢谢范教授的2位弟子。吴彪教授是我的好朋友，在那个为我校正译稿的时候，肯定是一个崩溃的过程，因为他得为我做很多的扫盲工作，给我讲解很多物理上的基础知识。同时呢，我也经常用那个微信推文骚扰他，给他问他很多那个伪科学的问题。他基本上是我这里的一个谣言粉碎机。我现在呢就想问吴老师一个可能有点幼稚，但是呢，我想大多数人都很感兴趣的问题，就是灵魂可能是物质的吗？因为刚才维尔切克教授在这个讲解的时候说过，就是在那个英国画家特纳画他那张画的时候，那个光还不是人们对光的认识，还不是它是物质的。现在我们都知道它是物质的，它是光子，它是粒子啊什么的。那么灵魂有可能是物质的吗
？Nietzsche is asking whether soul is a matter.
What are so
for me.
Oh, that's for you. Good, you can have it.
就是当我们物理学家，就是科学家来回答一个问题的时候，其实我们最关心的一个题是，比如说你是怎么定义灵魂，对吧？如果比如说你把灵魂定义成，比如说如果是你，比如说我如果把你的 DNA 定义成灵魂，那么从某种意义上你是有灵魂，因为就是说你拿着这个 DNA 来，你确实可以重新造出一个目标来，对吧？就是重新造出一个那个蓝莓来，对吧？你拿出这个来，你确实是可以做这件事情。但是我觉得传统意义上的那种灵魂可能应该不存在，因为传统上的灵魂好像还能记住他上一辈子在干什么。但这种在这科学里面，我想它肯定不是一个物质。但是如果你说我是不是有足够多的信息，然后来重新造一个目标出来，重新造一个蓝莓出来，那么现在我们其实确确实实已经有这个办法。那从这个角度上来讲，我觉得灵魂是物质，但是在传统意义上的灵魂肯定不是物质。
那么人的意志呢？人的意志是有这个能发生作用力吗？它和那个量子力学之间有关系吗？
就是人的意识其实是人的一个活动一个表现而已。就说就像你在这里运动，对吧？你在这里，你比如说你表演一个舞蹈，你会传递出很多信息来，对吧？这个东西它有一个物质的载体，就是你的表演，但是它本身传的这个信息，你不能把它叫做是一个物质。我的意思也是一样，意识无非就是你的大脑里的神经细胞在做各种各样的表演，表现出来的一个东西。这是我的理解，就是你去表演一个舞蹈，对吧？你有一个很具体的一个动作，但是不同的人、不同的舞蹈表达出的信息是不一样的。这同样的道理，你的人跟那个脑子里的那个神经元，它会有各种各样的反应，各种各样的物质的一个过程，化学反应啊，这种电的信号的传输，对不对？但是每个人通过这种活动会表现出来不同的思想、不同的意识，所以这种表现出来这个东西，我觉得它不是物质，但是你确实是可以感受到，就像人家表演舞蹈的时候，你确实能感受到那个舞蹈的美一样。这是我的理解。大家可以我想每个人可以有他自己不同的。
对，这每个人可以去理解，可以去思考一下。那个刚才那个3位科学家啊、物理学家，他们说的东西太理性了，我觉得我们那个大脑洞都有点成太脑洞了。所以现在咱们来点那个轻松一点的。那我问问钟一满导演，就是钟导呢，他那个是多年来从小就是音乐发烧友，他自己本身呢，也能演奏非常高超的、技艺精湛的小提琴。那个他呢，常年对这个音律都有很深入的研究，所以而且那个维尔切克教授的那个《美丽之问》里呢，也提到了毕达哥拉斯发现了音乐规律，并且呢，他也提到了天体乐章。所以我想问问 中导，就是音乐的这个规律，您认为这个音乐的对于音乐的这个意义是什么？或者说普遍的这个音乐性对于我们的意义是什么？
So he's asking the impact of the music to society for the as director, Steve. What does it mean for the life?
刚才咱们提了一个很大的问题，我想我把这个事情呢再往窄的放一点，就是说我们怎么感觉到音乐是好听的啊？就是这个问题还要再放窄一点，这就回到教授书里谈到，他说毕达哥拉斯就是希腊的哲学家最先提出来说，如果这两个声音呢，它们的振动比频率或者是旋长，呈这种简单小整数的时候，这两个呀就特别和谐。这个好办了，这个咱们谈这个问题就好办了。什么叫和谐？我们经常谈和谐。我今天什么和谐都谈，我就谈音乐的和谐，就谈音的和谐。什么叫小整数比呢？比方说哆和哆之间是2:1，他们俩的比就那么哆和嗦之间呢是5:2。5:3，哆和发之间呢，是好像是5:4吧，我忘了，反正是他们成这么一种关系，那么我想在座的一定很多人就知道，这个教授的书只谈到这儿为止。如果我们按照这个方法去把哆来咪发嗦拉西哆都找来的话，我们就出现了一种我们中国人叫做3分损律的这么一种哆来咪发嗦拉西哆，那么外国人也通过这个也找到了他们的哆来咪发嗦拉西哆，所以大家一直就这么唱，但是这么找出来的，往外找的时候，就发现慢慢就不那么协和了，一开始还是协和的，后来又不太协和了，不太协和了。欧洲人的中世纪呢，他们是那个宗教，他有个合唱团，他的合唱团呢就觉得，不那么和谐了，于是他就慢慢他们就体会到，原来这他们还要找这个简单小整数比，于是就找到了一种新的哆来咪发嗦拉西哆，这一套在这个音乐学上叫纯律，纯粹的纯，法律的律，纯律。那么他们唱起来呢就很和谐。然后呢，我们就发现，如果你去参加一个合唱团，老师会指挥，会告诉你，大家唱的时候往中间凑一凑，这个凑一凑就是要凑到纯，因为我们平常感觉不到，我们唱的那个那个东西是，比方说我给大家举例子，哆来咪，哆来咪，对不起，这就是不和谐的，那个咪就不和谐，应该是把那个咪降一点儿，叫哆，不是哆咪嗦叫哆咪嗦哆咪，和原来的哆咪嗦不一样。明白这一点，我们来看看这种新的纯律和我们唱的哆来咪发嗦拉西哆有什么不一样呢？你唱的时候，我教给大家一个诀窍，把咪、拉、西3个音稍微降一点儿，就是这个纯律但是呢，欧洲呢往下走出来，他不用这个纯律了，因为纯律也有它几个，它怎么整？它转调不好转，于是就用上叫12平均律。12平均律也是中国人最早发明的，明代一个叫做不叫红二代吧，就是黄二代，皇帝的那个后代，他发现的。那么，但是这个东西呢，几乎没有一个音是和谐的，但是它转调非常舒服。这个发明出来中国人听不到这个东西，所以也没有扩展起来。后来呢，欧洲人也发现了这个12平均律，于是他们的交响乐队就走向了12平均律，就离那个纯律远了。一直到什么时候呢？如果我们今天把那个老唱片 拿出来就听。 欧洲人原来从上世纪50年代以后又转回来了，又转到这个教授的这个就纯利了呀，他又转回纯利了啊。所以我记得当时有一件事情是英国的广播交响乐团和中国的中央乐团同台演出，一个人演一半，上半场你上半场我下半场，很多人觉得我们怎么与外国差那么多呀？其中一个就是我们没有使用我们没有使用这个服务。实际上，我们老祖宗也有纯利，但是我们没有这个教授书上这套什么小整数的小整数比没有这个概念。大家都知道，中国有一个很棒的一个数字题，就是曾侯乙钟，对吧？亚海钟，漂亮的来。当专家们去看这个钟的时候，突然发现说这是什么力？什么力？纯力。怎么出来的？中国人怎么找纯力？他张起一根弦，绷起来以后啊，一弹或者一拉，拿着手啊，轻轻的在弦上划过去，可不许按时了，不能按时了，轻轻划过去，你就大家可以用小提琴或者二胡来做这个实验，就发现有些音就出现了，各种音，中间没有，就到某一个地方，那个音就出现了。这个在音乐上叫泛音。摸到泛音，这些泛音的点和那个整个弦长的比就是小整数。所以中国人原来早就有这个东西，但是中国人没有这个数学理论，把它为什么是这么说呢？大家看，教授的书上有一个图3，有外国人也张起这弦，但是呢，他摁的是10音，但是他有尺子在那儿量。中国人呢就觉得谁耳朵好啊？盲人耳朵好，所以中国人在定像这个一些钟，古代出的这编钟的时候，他也张起一根弦，他呢用一个盲人去听，一个盲人的能量，他让这个人们去这样把这个钟给定出来。盲人更不可能去拿个尺子量了，对不对？盲人不可能拿尺子量。于是我们中国也有这个东西。我再举个例子，大家都知道了。古琴上不是底下有好多小白点吗？对吧？好多小白点，很多小白点上就是那泛音。你也可以按时了，但是你要是虚按一弹，就泛音。因此，我们发现唐代留下的一个曲子叫《幽兰》的时候，那个幽兰很多地方就是用2个泛音演奏，也就是这段曲子就是纯律的。专家们认为是这个纯律。现在问你那个钟啊，你摸的是有那个东西吗？我们能看你摸的那根弦吗？就在曾侯乙墓中处理的现场，有这么一个长的那个东西，上面还有这个小花。专家一看说这就是古代一直说的定音的那个军中定律，就这样绷一根弦的。这个发现只是大家可能没有注意到，我们中央电台做有关节目呢，那个编导呢也没注意到这儿，他这是最要紧的地方，对吧？这个没有这方面的报道，所以呢，我们国家开始从改革开放以后，我就说了，从英国广播公司的来以后，觉得不对了，我们也要这个向纯利靠拢，但是。实际上呢，已经有这方面的实践了。天津交响乐团来了一个指挥，这个中国的一个指挥，他就用这一套教授讲的这套方法来纯律来指导天津交响乐团。请问诸位谁知道天津交响乐团？都不知道。但是天津乐团演奏中国的旋律的时候，那个之好听之和谐，让专家全给震住。就是因为是纯律。注意啊，这套纯律要以纯律为主，别的还不能不用。比如说，大家知道《梁祝》演奏的是于丽娜演奏的，于丽娜就说过，我演奏《梁祝》就是用纯律。但是呢，有的地方还不能完全守纯律，什么地方？碰杯，就是这种中台，那个谁，中台碰杯的一闪了，那个时候是嗦西，然后到哆， 那个吸到刀之间要比纯利要小得多，就是哎呀推上去，哎推到那个刀，这个时候不是纯利，这个时候戏剧性很强，不能完全是纯利啊。这个我也是多说那么一句啊。所以呢，我们还有一个人也是使用纯利的，大概大家更是了解，但是谁都没注意到，就是台湾的那个邓丽君脸上，国内专家一听纯利啊。当然这个纯利呢，为什么一直后来在我们国家里没有推开？因为我们是跟苏联呢，它也属于欧洲那边，它也是五三分利。现在我们中央电视台播的女巨星那苏联来的都改纯利了，哎，他一改，北朝鲜就改，对吧？不叫北朝鲜，就是朝鲜，是吧？朝鲜就改，所以我们现在呢也要改。我们中央电视台呢对这个中国教育人团的指挥李新草大概都很熟悉，就专门有采访电视播。李新草说我们也要以纯利为主，来改动我们的这方使我们乐队和谐度大增加。
那个钟导，我插一句，就是说那个就是外国的交响乐到现在为止都是这么备受听众喜爱，是不是他们有科学的方法，还是说他们也凭着一种直觉？而我们
这个东西啊，有这样一个您提这个问题很好，就是说中央音乐学院毕业的这拉小提琴的人，你到欧洲去了，你想参加他们乐队，好，你先给我拉3个拉动，人家是按纯利听那种，就是按协同的听的。如果你拉不出这个纯利拉动，人也什么都不说，人家说哎呀可能不行啊。但是呢，中央音乐学院的有个老师，他就是学纯利的，他学纯利呢，就是马思聪都说他的音特别准。马思聪是从法国学回来的，法国那时候开始这个讲究纯利的，所以马思聪的特别平。他说你怎么会跟我拉出纯利的这个音阶来？他说我老爸就就会纯利。说你老爸跟谁学的？他说跟日本人学的。哦，这都从他这个下来了。因此，中央音乐学院毕业的学生到欧洲，如果你不懂得这套理论，没碰上这样的老师教你，对不起，你可能进不去乐队。你说我可能拿了一个大奖，我拿了什么大奖？对不起，你那个大奖是你的大奖，你现在要进乐队要讲结合，那就他妈不行。
那就是说，所以就是说，我们现在的这个文艺创作吧，文学艺术的创作都就是讲究科学的方法。您任职的中央电视台是国家的主流媒体，非常强调就是用科学的方法进行这个节目的创作。您能在这方面说一说您那个创作的过程中用的什么科学的方法？
我个人呢是想用教授的讲的这套方法做一套就讲中国的纯利的故事。就今天我给大家简单的讲这些东西，但是对不起，我已经退休了，所以呢，但是呢，年轻的编辑呢不懂这套，我跟他们说，他们太复杂了，没人到现在也没人做，我不知道在座的年轻人将来有没有来做。
因为我知道那个钟导做了几期这个节目，发现历史真相的节目，都是用的科学的方法，然后还获得了国家的电视节目的大奖，比如说这个下商周断代，和这个我就知道您用的是碳14的方法，还有就是这个光绪这改变清史的这个光绪死因的探索。
我讲刚才兰明先生提到的这个事情，我事先宣布一个，也不算秘密了，也算是秘密了。就是大家都知道光绪是不知道光绪怎么死的，这是在历史上大案。他死不到24小时，曾经他会死。那么我在专家们都认为光绪是正常死亡， 那么我在拍这个过程中呢，我发现呢，我就拿着他的头发到中国原子能科学院，中国原子能科学研究院去测试了一下砒霜出来他的头发，然后我就测试了他的内衣，包括外衣、绒袍都测试了大量的砒霜，所以呢，现在呢，国家也认可，就是包括我们国家的信息工程也认可，我们的这个测试是准确的，光绪的确是被毒死的。至于是哪一天给毒死的，几月几号几点下的毒，谁下的毒，这个现在已经出来了。我们这个书也出来，但是可能大家买不到，你这个在网上就可以想到了。这个整个这个测试报告，包括这个都出来了。为什么这个东西？我要说它跟文学艺术有什么关系呢？就是因为我测试光绪头发的时候，对呀，原子能研究科学院他们用的那仪器，把这个艺术就是中子打进去出来的那大白光，就看测出来这么多元素，里头有砷、氧化砷是砒霜。问题在于你怎么知道那就是砷呢？因为它那个测出来各种元素，对，高高低低，高高低低，几位专家都在这儿，那个高高低低是不连续的，没有中间的过程，这正是量子力学的伟大之处，就在于微观不连续，所以你永远测砷，永远它是那么高。永远它的能量永远是很大，所以呢，这一下就把砷找出来，砷找出来氧化砷，砒霜就找出来了。然后现在很多的，对呀，这个自然科学导致的这个科学连上，电影拍电影的拍电视剧的，赶紧找我们，我们来拍这段怎么样？这个太有意思了，这个光绪之死，最有意思的是我有个朋友，前一阵子他是在欧洲搞歌剧的，他说你们能不能写一歌剧啊？我说什么意思啊？那光绪之死，他说这样呢，我们可以专门为光绪死前，因为光绪从中毒到死中到发作还没死啊，中毒到发作是1个小时，1个小时。那么是不是有一大段光绪的死前的咏叹调？我说好，所以呢，我觉得要这么觉得，恐怕觉得是不是一个笑话？但是也确实如此，就是从量子力学的测试一直到最后的光绪之死或者还有一个咏叹调我不知道我这个回答是不是？
所以就是说用科学的方法发现了历史真相。那么这个科学研究的目的就是要发现这个我们宇宙的终极真相。所以我也想再问最后一个问题吧，想问这个维尔切克教授。So the scientific research is aimed to find the ultimate truth. I remember there was an American film called Few Good Men. Have you watched it? Few Good Men with Tom Cruise and Nick Jackson playing the main role. I remember the general played by Nicholson said, "You want the truth, but you cannot handle the truth." So I want to know. I want to know your opinion. When we human being finally find the ultimate unification or ultimate truth, can we handle it?
Can we handle the truth? Yes, I think we can handle the truth. It can be difficult for a scientist who has a beautiful, what they think is a beautiful theory or idea, to handle the fact that it might be wrong.
对一个科学家来说，就是说他非常担心的一件事情，就是他提出来的理论有可能是错的。
But science is a very simple game. It has only one rule.
但是科学呢是一个非常简单的游戏，它只有一条规则
which is that nature is the referee.
就是这个自然界是最终的裁判。
So there's that aspect of we have to like it or not, we have to handle the truth. There's only one ultimate arbiter of scientific endeavor, and that's whether the idea is true in nature or not.
所以无论你喜欢不喜欢，我们那个就是这个自然是我们最后的那个裁判者，就是我们的理论，我们的那个思想是对错。
So that's one aspect of the question from the point of view of individual scientists. A different aspect has to do with whether humanity as a whole can handle the kinds of truth that science reveals.
刚刚说的呢，其实是对一个科学家，一个单独一个科学家自己来说，他怎么来处理这个真相。现在，但是作为一个人类，能不能够面对真相？当我们科学家把这个自然界的真相展示在整个人类面前的时候，人类的未来如何处理这个真相呢？
And historically, this has not always been easy. Galileo was persecuted for teaching that the Earth went around the sun, for instance.
历史上这个其实我们有很多教训，比如说伽利略就因为教授这个地球绕着太阳转而受到了迫害。
And now some people feel threatened by the idea that we understand mind in terms of matter.
现在呢，有些人担心我们能够理解从物质的角度来理解思想。
Or threatened by the power of emerging kinds of technologies.
有些人会感觉到受到了那个正在发展的一些新技术的威胁。
And they can be very dangerous. Of course, we know about nuclear weapons.
当然，这些技术确确实实也可能也确实会带来一些破坏，比如说核武器。
We also have to worry about the possibility of biological weapons.
我们也必须担心一下生物武器的危害。
And weapons based on artificial intelligence.
还有AI 技术造出来的武器。
So each of these poses great challenges. They can, with power comes responsibility.
就是这些东西呢，都确确实实给我们提出了挑战。但是呢，就是说，一旦我们拥有了这个权利的时候，我们也需要有责任，必须有责任心。
So can we handle the truth? I think so, and I hope so, but I'm not sure.
能不能够面对这个真理？这个我希望是这样的。我希望将来确实是这样。
非常感谢今天各位嘉宾对我问题的回答。我呢想把剩下的时间呢留给主持人，也许呢观众当中呢有人也想跟嘉宾探讨一些问题。
These late this late.
非常抱歉大家，由于时间的关系，接下来我们只有2个提问的机会了。然后。
Can we have this lady and her daughter? They've been very engaged.
您先描述一下你的问题是提给谁的，然后用中文就可以。非常感谢教授给我这个机会提问的机会。我代表观众可以吗？首先非常感谢教授给我们带来一场非常好的科学与艺术结合的这样一个科普的教育。我呢本身是学心理学的，所以刚刚我对蓝莓教授、蓝莓老师所刚才提出的灵魂是物质的嘛，以及刚才听完教授科学与艺术这个结合的3个方面特别有感触。所以我的问题是提给这个教授的。刚才谈到这个灵魂是物质的嘛，那么我感觉科学与艺术，不管是哪个方面，包括我们音乐、建筑等等，都是我们人类对于宇宙的一个认识。不管物理学、心理学，都是来自于我们的哲学的思考，都是从哲学里边分化出来的。那么我们心理也是一样的，所以我感觉就是说，也许我们还没有发现这个事实，我们的灵魂、我们的心理其实也是一种物质，只是就像光那种光子的物质，跟我们目前所认识的物质不一样而已。所以我想问问教授，这个对于心理的也许在未来这个 对于物质的这个概念。刚才因为吴老师已经吴晓教授已经回答了这个概念，但是我有不同的理解，我想再问教授看他是对这个问题是怎么理解的啊。同时我有一个小问题，因为我今天带了我的女儿过来，所以我想知道这个对于科学家们，所有的教授都在这里，你们对于科学与艺术在未来的青少年教育的结合方面，你们有哪些更好的对我们家长的一些建议？谢谢。
So I just make it short. so she's a psychologist. So he's very. So you let me ask the question whether soul is a matter or not. So she wants to ask the question again, and whether soul is a matter or not.
Well, so far, most scientists who study the brain, and also most physical scientists, have been working under the assumption that matter is sufficient to account for mind.
就现在的科学家都认为，就是说我们的那个尤其是这些物质已经可以用来解释这个思想。
This might not be right, but so far the evidence is that it is.
这有可能不是对的，但现在的所有的证据都证明是对的。
So, for instance, specifically, when we do delicate experiments in modern physics, we have to make many precautions.
所以在我们在那个做很多那个物理实验的时候，我们必须有很多那个警告。
Because our instruments are so sensitive to all kinds of effects and do very accurate measurements.
因为我们的仪器对很多东西都非常敏感。
So we have to make sure that we hold the temperature constant, that we screen out radio broadcasts, and we compensate for shaking of the earth. We have to, in many cases, keep the rooms very clean, work in vacuum, work at very low temperatures. They take many precautions.
对，我们做实验的时候需要做很多那种准备，就是把噪声给去掉，比如说，让那个温度非常的平稳，让那个就是让那个比如说那个地球会震动，我们怎么把这个震动给去掉？这些所有这些有可能带来的噪声，我们就把它给。
But one thing that people have never had to worry about so far is what anybody is thinking about it.
但是其实虽然我们在做实验的时候需要做非常小心，把这些很多那个很小的噪声给考虑进去，但是我们做实验的时候从来也不需要考虑你怎么想，你无论怎么想，实验都是一样的。
So if mind has an effect on matter, it must be a very subtle one.
所以如果这个思想对这个物质有什么作用的话，这个作用应该非常的就是说微妙，没法测量。
If there's a separate one that we don't don't already take into account, we haven't encountered any manifestation of it.
就是如果它没有作用的话，我们至少到现在为止没看到。
On the other hand, we've also learned in recent years that matter can do very surprising things.
最近呢，我们也会发现这个物质呢，其实表现得非常的神奇、奇怪。
It can make lasers, it can make superconductors, it can make televisions and smartphones, all kinds of clever things.
对啊，比如我们现在制造的所有的这些技术，就是那个激光、超导材料，还有这个都是我们建立在我们对物质的理解上。
Perhaps most relevant and most impressively, we can make computers that do things that people would have thought required minds to do.
对啊，比如我们现在比如最神奇的就是说，我们现在可以让计算机做一些我们认为以前只有思想才做的事情。
Like play chess very well or play Go very well.
比如说现在计算机那个下围棋、下象棋都非常厉害。
And we know exactly how those things are made because we made them.
我们都知道这个，就是说怎么这个就打败人类的这些计算机在下棋、下围棋的时候打的这些，我们都完全知道它是怎么造出来的。
Based on the principles of physics and science.
就是我们造这些机器的时候，造这些计算机的时候，编这些程序的时候，都是用的是物理的定律。
And we didn't have to give them a soul.
我们不需要给他们。
So maybe we'll find that eventually, to account for how nature works, we'll have to reintroduce souls, or to make really smart artificial intelligence will have to somehow produce souls, but so far there's no sign of it.
将来我们可能造出一个人工智能，或许它真的有灵魂什么，但是到现在为止没有看到任何一个迹象。So she has a second question. Is her daughter.
Yes.
So whether you have any advice
that she has
for her education in terms of arts and science?
Well, the main, I think there are two aspects. One is that she should explore very widely. There are so many interesting things in the world that.
他有两个建议，第一个建议呢，就是他应该非常广去涉猎各种各样的活动、课程。
And things change so fast that there are many new opportunities for young people to take up, and it can be bewildering to try to keep track of them. But I think by keeping open and going to reading, looking on the internet, you can find many things and get interested and find something that you fall in love with.
这个世界变化非常的快，而且发展的非常快，所以呢，你必须得保持让自己开放，愿意去接受新的事物，愿意去探索各种各样不同的话题。
So I would certainly recommend exploring very widely.
所以我非常建议你去多涉及各种多涉及、多看、多读。
But complementary to that, you have to learn basic skills.
在这个基础上，你必须学一些基本的技巧。
So if you want to go into science, you certainly have to learn about mathematics as soon as possible.
比如你想学科学的话，你就必须尽早的学数学。
To go into art, you should learn about drawing and practice.
比如你要从事艺术的话，你就必须从小学练习绘画基本技巧。
To learn about music, you should also practice.
比如你要学音乐的话，你就必须不停的练习。
So you have to master the basics, and the sooner you can do it, the better, because it's like learning a language. To make it your own, so you can be fluent, you have to learn it. It helps to learn it at a very young age.
所以就说，你为了掌握这些技巧，你就是尽早开始，而且练习的越多，也越熟悉，成为你身体的一部分。
And one more piece of advice is to study history and read biographies, because you can learn about the experience of people in the past who've been successful and can inspire you.
另外一个就是从历史来学习，就是去读那些传记，从以前人的经历，他们怎么成功的，从那里面能够得到很多的经验，学到很多东西。
As well as people who've made mistakes and overcome them, and people who've made mistakes and not overcome them. You can learn from these things.
你也可以从以前人犯的错误里面学到很多东西。
接下来还有4个机会，然后那个有2个要求，第一就是把你的问题尽量简短的描述，第二就是只问一个啊，一共只问一个。So, how about you?
The lady, and then yeah. Yeah.
My question is,
I can't hear you, so.
you can hear me? Can you hear me?
Barely, yeah.
Okay, and my question is, we know that you used to said that during the scientist, Stephen Hawking said that maybe few days later the artificial intelligence will maybe就是未来 AI 可能会就是比人类要或者说战胜人类，但是您今天的报告里讲的都是比如说音乐、建筑和绘画，还有这些就是其中蕴含的科学的道理。那么我的问题是，就是科学和艺术这两个东西，就是他们的关系究竟是什么？是说他们是先从艺术里有的这些科学道理，还是人发现的这些科学道理？ my question, the only question is the relationship between the scientist and the comes first. We find the science from the arts, or we create the arts. We create the art by the science.
Well, I think.
Regulation.
Okay, I think this is a similar question to which came first, the chicken or the egg. It has no single answer. I think scientists can be inspired by art, and artists can be inspired by science. And I think historically, probably art came first, but now, but thinking carefully about the world and recognizing regularities. Well, maybe art didn't come first. Maybe they arose together, and I think they're both important parts of the human experience, and they work hand in hand. So, I think both go back. Both are in the nature of human beings, and go back to when human beings first arose. So I'm not sure which came first. But,
就是他这个问题的答案，就是说，其实就是和鸡和蛋到底是不是生一样的，这是一个基本上没法回答的问题。
But they both go back to the beginning.
他们在人类历史的最早都出现了科技，人类这个即使说既有科学活动，也有艺术活动。我们艺术家和科学家互相鼓励，互相。
谢谢主持人，非常感谢弗兰克教授给我们带来的精彩报告。我的问题还是关于灵魂的问题。这个，我想继续追问这个。我们就说，先不说灵魂是个有争议的概念，有的很多人不承认有用。我们就说这个意识，我对这个问题一直就是说有兴趣。这个人的意识是怎么来的？按过往的观点，就说意识是大脑的产物。实际上，现在以后有科学，包括佛教、宗教一些佛教里面，意识是另有来源的。意识不是是从大脑里产生出来的，意识是有另外的来源。现在有很多关于科学上的研究，就是说有濒死体验的研究，就是人在濒死，就是说一个人就是说发生车祸了或重大疾病，然后因为医学上把他救活了以后，他有濒死体验，他的灵魂离开肉体去干嘛干什么，有很多这方面的研究啊。然后呢，还有很多关于前世记忆的研究，一个人他他回忆起自己的前世在哪。美国有一个纪录片叫生死与轮回，也是科学家，我忘了那个科学家的名字，生死与轮回就是说，我就想，发现这个意识在科学上怎么来看待？它是有的人说意识是一种量子现象有量子纠缠的什么的。那么我想就是说问一下弗兰克教授就是说你对这方面对意识的这个起源来源您是有这个兴趣，你关心过这方面的问题没有？
So his question is very long, but I try to make it simple. Basically, he wants to what is conscious?
What is consciousness?
Yeah, and how it's related to matter, and whether the consciousness is a quantum phenomenon.
Okay, consciousness is a very interesting subject that has recently started to be illuminated by science.
这个意识是一个非常有意思的过程。现在的科学家正在揭示它的那个真面目。
And there are some very interesting discoveries that have been made, but it would take quite a while to explain them.
最近呢，对这个意识有很多发现，但是我这个就需要一定的时间才能解释。
But to oversimplify quite a bit, what's emerging
就是这个让我用最简单的那个方式来解释。
is that although we feel that we are conscious beings in control of our activities and opinions,
尽管我们有意识，我们能够控制我们的行为，控制我们的意见。
In fact, there are many deep processes going on in our brain that kind of report to consciousness.
在我们的那个大脑的深层呢，其实有很多活动，能够就是说和意识是相关的。
So consciousness is more a receiver of reports than a maker of decisions.
意识其实是一个更是一个报告者，而不是一个接收者。
So far, as I said before, there's no evidence of a separate soul or consciousness apart from matter.
我刚刚已经说过了，在物质以外是没有独立的灵魂和意识。
And we're beginning to understand that consciousness might be produced by regular brain activities in ways that are beginning to be understood, but it's early days yet.
我们科学家正在理解这个意识是怎么在人类的大脑当中产生的，但是这个研究呢还属于早期阶段。
And I don't think it has anything to do with quantum mechanics.
它和量子力学没有任何关系。
The brain is very. Okay. Should we?
就是如果下面大家还有什么关于意识啊、量子啊，还有这个灵魂的，我们就不用再问了。那个，要不接下来的2个我们选这边。
She wins because of her performance.
对。
Hello, Professor Wilczek, and I have a question. Now I am 10 years old and I have learned a bit of physical science, just like molecules and atoms, and I really like it. So did you like physical science when you were little?
Yes, I certainly did.
Why did you like it?
I'm not sure, I just did. Some of my very earliest memories are about taking things apart and putting them back together. And I like to play with big numbers. And it's just interesting. And if you find those things very interesting, keep at it. It's a gift and can lead to a very wonderful and fulfilling life if you follow through.
What do we have to do if we want to be good at physical science?
Well, you have to stay curious. You have to acquire basic skills. As I mentioned before, you really have to pay attention to mathematics and learn that. Read in whatever subject you're interested in. Play around, do experiments, explore. It's not a magic process. Just immerse yourself into all the sources of information and inspiration you can get. Read biographies of great scientists, read about the history of science. I think you're probably of the right age to start thinking about reading Richard Feynman's book, The Character of Physical Law. So that would be a good introduction.
Okay, so is mathematics sort of like the building blocks of physical science?
Mathematics is an essential tool in modern science. And mathematics broadly conceived, so it also includes being literate on computers, knowing how to access information with computers, but knowing how to use statistics, mathematical tools. Yes, that really what we've learned is that the language of nature is mathematical language, and if you want to understand nature deeply, there's no avoiding it. But it's also an opportunity because it can be very beautiful and fun.
Thank you.
Thank you. She invited me.
On the back.
I will start.
Okay, this man
Sorry,
here.
Professor.
Who's speaking? Someone's speaking.
Yeah.
Oh, okay.
Yes. Thank you for your amazing, amazing presentation. And I'm currently studying physics, so I want to ask you a few things about physics. So we know that many times in modern history, many theories like your quantum cryodynamics is drawn from empirical evidence, and we need to verify them by producing concrete evidence. So is there something that leads you to believe that we might, or some
methods that we might devise a effective, concrete, and easy experiment to verify our theories and leave it real well verified?
Well, it varies from case to case. And some theories are easy to test. Sometimes it takes a long time to test a theory. Sometimes when you finally do test a theory, it turns out to be wrong. I mean, we have experience that's different in different cases. So QCD, at first the evidence was kind of tenuous. It was based on bold interpretation of a few experiments. But now there's mountains of evidence and very accurate experiments, and that process took 10 or 20 years to go from a rough idea to a mature theory. Electrodynamics, when Maxwell discovered it, what we now think of as modern electrodynamics was not widely accepted, and it was only when Hertz, about 30 years later, made electromagnetic waves that people accepted it. The Higgs particle took almost 50 years to discover, and so sometimes things take a long time. Sometimes it's very fast. When T.D. Lee and C.N. Yang proposed that parity is violated, the experiments were done within a few months. So it varies from case to case. I'm still waiting for axions, anyons, which are a particle I introduced just now are being developing into a rich theory and experiment after about 30 years. Time crystals, when I first introduced them 6 years ago, were very controversial and thought to be impossible, but then they were discovered last year or so. So it varies from case to case, and it's very interesting to study history.
Thank you. And well, I mean, this lecture or this presentation almost turned mythical, like when we were asking questions. So I want to say, just in my mind, is it true that only those theories that can be proven wrong are valuable, or let's say meaningful to be discussed or tested? If we have theory that we cannot prove it wrong, we cannot either prove it correct, but we just think it as a theory, then there's no need in discussing it, right?
Well, as I said, science is a game with only one rule, which is that nature is the referee. So nature, no matter what, if you think your theory is attractive and beautiful, that's not enough. You have to show that it describes nature in order for it to be a validated scientific theory. I believe this very strongly. But even beyond the question of truth, there's a question of fruitfulness. If you have a theory that does not explain anything concrete about nature, it's a theory that's not very valuable. Right? It's at least as a theory of nature. It may be valuable as mathematics or as art, but it's not valuable as a description of nature. So yeah, I mean, to me, physical theories take on another level of interest and importance when they lead to an enhanced description of what actually happens in the world.
Yeah, and this year I studied with Professor Gunter Noland, who is also at MIT, and I studied like the jet production in LHC and Atlas. So I guess I probably contributed a part to using.
Very good. Congratulations. Thank you. Okay. Well, you from the yes.
So the girl or the boy?
Well, first the boy, then the girl. Okay. And let's try to keep the questions short, and I'll try to keep the answers short.
建筑和绘画都是关于空间的艺术，但是物理呢是关于时空的艺术。那我的问题是，时空的合理性和 空间中和跟相比有没有比较特别和不一样的地方？谢谢。
Architecture and art is about the symmetry in space, but science is about the symmetry in space-time. So it's a relation.
Yes, well, 就时空上对称和空间上对相比有没有不一样和特别的地方？
He wants to know the difference between them. The symmetry in science is about space and time, and the symmetry in art and architecture.
Well, symmetry in science is a very, very versatile tool. So, for instance, the study of crystals, ordinary crystals, is about symmetry in space.
是时空上对称，不是科学上的对称。
也就是说，
就四维时空上的对称和三维空间的对称相比。
He wants to know specifically the difference between the symmetry in space-time, just four-dimensional space-time, and three-dimensional space.
Well, it's the same concept. It's the concept of change without change. So the difference really is not very much.
那个基本的概念其实一样，就是不变之变，就是其实没有什么。
时间并没有什么特别的地方，只是单纯增加一个维度是吗？
He's asking whether the time dimension is just a trivial addition of another dimension.
Well, the time dimension, it's proved very, very fruitful and informative to treat time as another dimension in physics.
就是说，在物理里面，我们把时间当作另外一个维度，确实是给我们带来了非常很多深刻的理解。
And that was an important thought, especially introduced in the theory of relativity.
这是在那个相对论里面引入的一个概念。
But it's also just a fruitful way of thinking about systems that have dynamics and change in time.
这也是让我们能够更容易想象一下这个系统在演化的时候。
So, like in Feynman diagrams, we draw time as just another direction in a sheet of paper. And that's very common in calculus to write motions as movements through time.
在微积分里面，我们也经常会把运动描述成是时间的变化。
So we're very, very accustomed to and comfortable with the idea of treating time as another dimension.
所以我们其实是早就在把时间当作一个。
But it's not literally the same as space. It has some special features, of course.
当然，它和空间还是有区别。
And I'll just conclude this answer by saying that understanding the nature of time in quantum mechanics is a very important frontier of modern physics that's not fully explored.
就是说我最后想说的事情是，就是说在量子力学里面去理解时间，其实是一个刚刚开始的一个方向。
The fact that time crystals emerged so recently is an example of the fact that we still haven't fully understood the nature of time.
我最近提的那个时间晶体 time crystal， 其实就是在展示，就是说我们在量子力学里面对时间这个维度还远不够。
And there are many other aspects of how time figures into quantum mechanics, which we're actively exploring, which I think will be an important frontier of research in physics in coming years.
就现在我们量子力学里面，我们就都在研究跟时间相关的很多物理，将来可能会。
I want to ask a question. Besides your scientific research, how did you combine science and arts in your spare time?
Well, I'm especially interested in music myself. I play the piano, and I enjoy listening to music and learning about music. This has been something that I've done since childhood. I played musical instruments, but really it's only in adulthood that I got a more serious interest in music and its formal structure. But So that's something I enjoy doing. I don't know what else to say.
维尔切克教授他业余时间非常喜欢音乐，他从小就弹过练过乐器，然后但其实真正到了成人的时候才开始真正去思考。
I've learned to be much more interested in visual art than I was as a teenager or a child, but I'm still not very good at drawing.
我现在呢，比我在十几岁的时候要更喜欢视觉的艺术，比如说画画，但我依然非常笨拙，我画不好。
谢谢。
Okay.
由于时间的关系，我们今天确实不能再让大家提问题了。那么今天的活动就到此结束。我们在这里非常感谢维尔切克教授以及其他的音乐专家。然后最后就是对科学连线这个活动感兴趣的同学们，可以关注中国数字科技馆以及环球科学的这个网站或者新媒体平台。我们接下来还会有陆续这样系列的和著名的国外的教授对谈的活动。然后同学们也可以去访问中国数字科技馆的网站，这是一个科普平台，上面有很多科普的视频、动画，然后以及其他的多媒体材料，上面还有很多科学的课程，然后以及课外的活动。好，今天就到这里，谢谢大家。